Okay, so in this video, we are going to learn about series and parallel circuit. So this is a back-to-back solution from complex circuit to a simple single equivalent circuit. So we are going to use KCL and also KVL. So in this video, we have these circuits, and first thing to do is we need to analyze our circuit. So we have R1 to R8. So we need to check the relationship of each resistors in the entire circuit. So as we observe, R5 and R6 are parallel. Also, R3 and R2 are also parallel. So from this case, from this situation, we can now start solving our circuit, converting from complex to a single simple equivalent circuit. So let's say this is our case 1 and we have case 2. So we have here on the right side the equivalent circuit diagram and the number of cases that we are going to solve. So let us start. So we will start on the first case. So case 1, we have 1 over the equivalent circuit is equivalent to 1 over R2 plus 1 over R3. So this is R2 parallel R3. So we have 1 over 45 ohms. So as you can see, R2 is 45 ohms plus R3, we have 1 over 30 ohms. So this is to the negative 1. So our equivalent circuit, or this is our R2 parallel R3, is equivalent to 18 volts. So please check on, if you have your calculator, you can check the answer. So let's label this one. Next is we will solve for case number 2. So case number 2 is R5 parallel R6. So for case number 2, R5 parallel R6. So the same manner, so we will have the equivalent circuit or equivalent resistance. We have 1 over R5 plus 1 over R6 to the negative 1. So this is equivalent to 1 over 15 ohms plus 1 over 60 ohms. So this is R5 parallel R6, and that is equivalent to 12 ohms. Okay, so we are done solving the two cases. Now let's draw the equivalent circuit. So from the complex, we will convert this one into a simple single equivalent circuit. So we start from combining the case 1 and case 2, and this is now the circuit. So we have, again, this is our 30 volts. Okay, let's just copy the entire circuit to save time. So this is our entire circuit. And so this is not the equivalent circuit. So we'll just delete this one. So we don't have this circuit anymore. Also this one. Okay. Now, this is our R2 parallel R3, and this is our R5 parallel R6, which is equivalent to 18 and 12 ohms. So this is now 18 ohms and this is now 12 ohms. After that, we have our third case. So as you can observe in this circuit, R2 parallel R3 is 1, R5 parallel R6, and R7 are in series. So this is now our new case. So shall we say this is our case number 3. Okay, so for case number 3, we can have R2 parallel R3 plus R5 parallel R6 plus R7. So we have the equivalent resistance, which is equivalent to 18 ohms plus 12 ohms for R5 and R6, and we have 20 ohms for R7. So the equivalent resistance is, it will total of 50 ohms. So just check on the value. So this is equivalent to 50 ohms, and this is our okay. So this is equivalent to our R2 parallel R3 plus R5 parallel R6 plus R7. Okay, so we already solved the third case. Now, with this, we can again convert our circuit from a simple circuit. So let's just copy this one. Okay. And this is now the circuit. So let's delete this one. And we have now our equivalent circuit now. So this is our R2 parallel R3 plus R5 parallel R6 plus R7, which is equivalent to 50 ohms. Okay, so let's write the color. Okay, so that is the equivalent circuit. Let's just adjust font so that we can see it clearly. Okay, so this is now our equivalent circuit for after solving case number 3. Then after that, we have now our case number 4. So our case number 4 is, as we observe in the equivalent circuit, we have R4 parallel to R2, R parallel R3, this one. So the R4 is parallel to the 50 ohms resistor. So this is our third case. Okay. So shall we say, rather this is our case number 4. So for case number 4, we have R4 plus this circuit, this equivalent resistance, this one. Okay. So they are in, no, they are in parallel, not series. So they are in parallel. So case number 4. So we can just compute for the equivalent circuit. So we have 1 over the equivalent resistance is equal to 1 over 50 ohms plus they have the same resistance 50 ohms to the negative 1. So this is equivalent to 25 ohms. 25 ohms. So this is okay. So that we can have. So this is now 25 ohms. So we already solved for case number 4. After that, we have now our equivalent circuit for this. So we can have now our new equivalent circuit. So this is now our equivalent circuit. And this is 25 ohms. This one. Okay. So our equivalent circuit now is 25 ohms. Then after that, we can now therefore have our case number 5. So our case number 5, it is obvious R1 is in series with R8 and also the previous equivalent resistance, which is 25 ohms. So we can now have case number 5. So it will now convert, the complex circuit will be now converted to a simple single equivalent resistance. So we can now have R1 plus in series with this one plus this is in series with R8. So the equivalent resistance now is, or our total resistance is equivalent to 25 ohms plus 25 ohms plus 10 ohms. So our RT is equivalent to 60 ohms. Okay. And the equivalent circuit now, we have, this is now our 30 volt supply. And we have now our equivalent circuit, which is REQ or R total, which is equivalent to 60 ohms. Okay. This is 30 volts, positive, negative. Now, after solving for the total resistance, we can now solve for the total current that is flowing in the entire circuit. So, since we have now our RT, we can now solve for the total current in the entire circuit. So to solve, we already know that V is equal to IR. So we can now solve for IT, which is equivalent to V over R, VT over RT. And this is equivalent to 30 volts over the total resistance that we computed earlier, which is equivalent to 60 ohms. And therefore, our total current is equivalent to 0.5 ampere. Meaning, there is a 0.5 ampere that is flowing in the entire circuit. So this is 0.5 ampere. Now, from this, we can also say that 0.5 ampere is the same current that is flowing in R1, the equivalent resistance for the parallel R4, parallel R2, R3 plus parallel R5, R6 plus R7, and also for R8. So the current flowing in the entire circuit is equivalent to the current which is flowing on R1, R8, and this 25 ohms resistance. So because of that, we can say that IT is equivalent to IR1, which is equivalent to IR8, and also IR4 parallel to R2, R3, plus R5, R6, plus R7. So all the current that is flowing in these resistors are equal since they are connected in series. Therefore, we can now solve for the voltage drop across these resistors, these three resistors. So we will solve now for voltage, solve for voltage drop across VR1, VR8, and also VR4 to parallel R3 plus R5 parallel R6 plus R7. So we have VR1, IR1, and VR1 is equal to 0.5 ampere multiplied by the resistance of R1 based in our given circuit, that is 25 ohms. This one. So we can have 25 ohms. VR1 is equivalent to 12.5 volts. Okay. And we can also solve for VR8. VR8 is equivalent to RA. So we have 0.5 ampere times the resistance of R8. You can remember, R8 is equivalent to 10 ohms. So 10 ohms, that is equal to 5 volts VRA. After that, we can also solve for the voltage across this resistor, the equivalent resistor. So we have now I times R. So we have they have the same currents, and since they are connected in series, and the equivalent resistance for this REQ is equivalent to 25 volts. So this is equivalent to 12.5 volts. Okay. So this one. So I'll just copy this one so that we can have. Okay. So we already computed the voltage drop across the simple, the equivalent circuits for R1, this REQ, which is equivalent to 25 ohms, and the RA. So by that, we can also check using the Kirchhoff's voltage law. According to Kirchhoff's voltage law, or KVL, the summation of all voltages is equivalent to 0. So for Kirchhoff voltage law, the summation of voltages is equivalent to 0. So that is according to KVL, or Kirchhoff's voltage law. So let us look into our entire circuit. This one, okay, as we already know, the voltage across all these resistors. So we have a voltage drop here, which is equivalent to 12.5 volts. Also, we have also a voltage drop here, which is equivalent to 5 volts. And also the voltage drop here, which is equivalent to still 12.5 volts. So checking this entire circuit, if the Kirchhoff voltage law will be satisfied, so we can draw an equation for this one. So we have VR1 plus VR8 plus VR4, which is parallel to the R2, R3, plus R5, R6, plus R7, minus the voltage total. So minus VT, which is equivalent to 0. So we have VR1, which is equivalent to 12.5 volts, plus VR8, voltage drop on resistor 8, that is 5 volts, plus this voltage drop on this resistor, which is again 12.5 volts, minus our source voltage VT, which is equivalent to 30 volts. And it satisfies the condition that the summation of voltage on a circuit is equivalent to 0. So 12.5 plus 5 plus 12.5 is equal to 30 minus 30, and that is 0. Okay. Now, because of this idea, we can also solve for the current across IR4 and also the current across this equivalent resistance, because we already know the current flowing in the entire circuit. We can now solve for IR4 and IR this equivalent circuit. So we have, since this is equivalent to 12.5 volts, so we can compute the current across I4 or resistor 4 and the current across this resistance, equivalent resistance, which is equal to 25 ohms. Now, we already know that the voltage across this resistor from the two resistor is 12.5 volts. Therefore, since they are connected in parallel, we can say that the voltage drop across VR4 is also equal to 12.5 volts. And also the voltage drop across the REQ equivalent circuit, this one, is also 12.5 volts. So this is, so we can now compute for the current across IR4 and this equivalent resistance or resistor. So we have, so solving for IR4 and also solving for I equivalent circuits, or this is equivalence in R2 parallel R3 and also R5 parallel R6 plus R7. So it's current for this one. So we have IR4 is equivalent to 12.5 volts all over 50 ohms, and that is equivalent to 0.25 here. And for REQ equivalent circuit, we have 12.5 volts. So I am talking to the current across here. So all over 50 ohms. So we can have equal, it is still equal to 25.25. So this is now the current that is flowing here and also the current that is flowing here. But we need also to analyze the current that is flowing in the entire circuit. We will check also for the current flow of the entire circuit. So what are the currents that is flowing in the entire circuit? So let's just analyze the flow of current here. So we have our total current that is flowing here. So let's say this is the IT, which is equivalent to 0.5 ampere. And we have current here, and that is I1 across R1. Also, this is equivalent to 0.5 ampere. We have our current here, that is our I4, and that is equivalent to 0.25 ampere. This is our, and also looking into point A, junction A, there is also a current going up here, and also there is a current going also here. Then shall we say that this is I3, and also this is I2. So the I3 will flow here, and there's also a current that will go out from point B, and there is also another current that will go down here. So let's say this is I5, and this current is I6. So this is also I6. So the same current that will go down here, we have I6, and we have also another current, we have I7. So I5 and I6 will meet on this junction at point D, and the resulting current will be I7, and there's last current that will flow in our circuit, and that is our current I8. Okay, so let's go back to our circuit so that we can check this one, case 3. Okay, so let's copy this one. Okay, this is now a circuit. Now, R2 parallel R3, R5 parallel R6, and R7 are in series. So therefore, so this is the current, 0.25 ampere is the current that is also flowing for R2, R3, R5 parallel R6, and also R7. So R2 parallel R3. So 0.25 is flowing in this series resistors, R5 and R6, and also the R7. So therefore, having said that, having that idea, we can now solve for the voltage drop across resistor or the equivalent resistance, 18 ohms, 12 ohms, and 20 ohms. Okay, follow? So solving for the voltage drop is easy because we already know the current across the 18 ohms, the 12 ohms, and the 20 ohms resistance. So we have now VR2 parallel R3, IR. We already know that is 25 ampere, and this is 18 ohms. By the way, later on, we will validate these values in a simulator so that we can check our computation based on the simulation. So I will present to you the simulation of this circuit so that we can validate our answers. So we have now, that is 4.5 volts. Okay. For VR5 parallel R6, the same current that is flowing in this circuit. So we have 0.25 ampere multiplied by the equivalent resistance, that is 12 ohms, and this is equivalent to 3 volts. And for VR7, we have IR, and that is 0.25 ampere rather, multiplied by the 20 ohms resistance on R7, and that is equivalent to 5 volts. So we have now our voltage drop across this resistance, and this resistance. So this is 4.5 volts. We have also 3 volts for R5, R6, and we have 5 volts for R7. Now, since R2 and R3 are parallel, therefore voltage across R2 and R3 are equal. Since R2 and R3 are parallel, so we can draw again another. So this one is, we have VR2, which is equivalent to 4.5 volts, and also VR3 which is equivalent to 4.5 volts from our circuit here, this one, because R2 and R3 are parallel. So since the voltage across here, R3 and R2 is 4.5, therefore R2 is equal also to 4.5 volts, and the voltage drop across R3 is also 4.5 volts. Okay, so let's go back. And also, since R5 and R6 are parallel, this one, and based on our computation that the voltage across this equivalent resistance, which is 12 ohms, is 3 volts, therefore we can also say that VR5 is equal to 3 volts. And VR6 is also equal to 3 volts. Okay? And because of that, we can now compute the currents on the entire circuit. So I am referring to this current, I1, I3, I2. So all of this current that is flowing in our circuit. So this one, also this one. So we can compute now. Actually, using Kirchhoff voltage law, looking into point A, point B, point C, point D, we can also solve that one. So on the later part. So, okay. So for VR2 and VR3, since they are the voltage across these resistors are equal, so we can solve for the current. So here, and for this one, so IR2 is equivalent to 4.5 volts over the resistance across R2, which is equivalent to 30 ohms. So in our circuit, so this one, 30 ohms. And that is equivalent to 0.15 ampere. For IR3, we have 4.5 volts all over the 45 ohms resistance, and that is equivalent to 0.1 ampere. Now let's move for IR3, IR5. So IR5, so we have 3 volts voltage drop across resistor R5 and resistor R6. So they are equal since they are connected in parallel all over the resistance across R5, which is 15 ohms. And that is equivalent to 0.2 ampere. And for IR6, we have 3 volts all over 60 ohms resistance. So we have this one, 60 ohms resistance, and that is equivalent to 0.05 ampere. Now, it is obvious in VR7 that IR7 is equivalent to 5 volts all over 20 ohms, and that is equivalent to 0.25. Okay, so this is now the values of our current. So this is IR7, IR6, IR5, IR3, IR2. So we can also solve for I8 using the Kirchhoff's current law. So let us look the 4 points or 4 junctions in our circuit. So let's copy this one for better visualization of the problem. And let's paste this. Okay. So we have now our entire circuit here. Okay. So let's check. Let's project looking at point A. So using KCL. So according to Kirchhoff's current law, that current entering is equal to the current leaving, or this is equal to I input is equivalent to I out. So entering is positive. So we can have this symbol entering in a point or in a branch is positive sign, leaving is negative. So looking at point A, we can draw equation. So as we observe, IT is entering branch A, and also there is a current leaving from branch A, which is I3, I2, and I4. So there are 3 currents that is leaving away from point A, and there is also a current entering towards point A. So we can write the equation I1 and the 3 leaving circuit away from the point A minus I3 minus I4 is equivalent to 0. Now substituting the values of this I based on our previous solution, so we have I1 is equivalent to I total, so we have 0.5 ampere minus I2. So what is I2? We have 0.15 milliampere. So 0.15 milliampere minus I3, which is equivalent to 0.1 ampere. So 0.1 ampere. And the I4, which is equivalent to 0.25 milliampere. So I4 is equivalent to 0.25 milliampere. So we can compute actually okay, here, this one. I4 is 0.25 milliampere. Okay, so let's substitute the value 0.25 ampere. By the way, ampere not milliampere is equivalent to 0. So we have 0.5 minus 15 minus 0.1 minus 0.25. So on the left side of the equation is equivalent to 0 is also equal to on the right side. So it satisfies the condition or the statement of KCL that the current leaving is equal to the current entering. So the summation of all current in this point at point A is equivalent to 0. We can also validate looking into point at point B. So let's validate looking at point B. So we have I3 as the entering current. Also, we have I2 entering current, and the leaving current is I5 and I6. So we have this one, I6, I5 going downward, and yes, we have I3 also that is entering, and that is entering at point B. Is equivalent to 0. So we have I2 which is equivalent to 0.15 ampere plus I3 which is equivalent to 0.1 ampere. We have I5 that is equivalent to 0.2 ampere. So minus 0.2 ampere. And for our I6, that is equivalent to 0.05 ampere. 0.05 ampere. That is equivalent to 0. As we subtract the summation of all currents at point D, so we have 0 also. So we satisfied the condition. Looking at point C, and also looking at point D. So let's look first point D. In point D, we have I6 and I5 entering the point. So we have I5 plus I6 minus the current leaving away from point D, and that is I7, that is equivalent to 0. So we have I5 that is equivalent to 0.2 ampere plus I6 that is 0.05 ampere minus I7. So what is our I7? We already know that the voltage drop across I7 is 5 volts. So this one, so that is 0.25 ampere minus 0.25 ampere is equal to 0. So as we compute this one on the left side of the equation, again, this is still 0 and it satisfies the condition. Now, let's solve for what is the value of I8 now. So we can solve for the value of I8 using the Kirchhoff's current law. So we have leaving current is I8 away from point C, and the entering current, directed current towards point C is I4 plus I7, which is equal to 0. So I8 is negative since it leaves away from point C. So we have now substituting the equation plus I4. What is I4? I4 is equivalent to 0.25 ampere. So this one, where we first solved the IR4. So this one. Then our I7, which is also equivalent to 0.25 ampere. So plus 0.25 ampere, that is equivalent to 0. Substituting or transposing the equation, it will result to I8 is 0.5 ampere. Okay, so I8 is also equivalent to IT. So this is the same current that is flowing in the circuit. So we have this current going here. So that is the current that also flowing in the entire circuit. So we have now the values of this current. So we have I3, which is equivalent to 0.1 ampere. I2 is 0.15 ampere. Then we have I5 is 0.2 ampere. I6 is 0.05 ampere. And we have I7 that is equivalent to 0.25 ampere. And our I8 is 0.5 ampere. So as you will observe, the current entering is equal to the current leaving. The current that enters the entire circuit is 0.5 ampere, and it satisfies the condition of Kirchhoff's current law that the current leaving also is equal to the current entering, which is equivalent to 0.5 ampere. Okay, so we already solved our complex circuit, converting it from a single simple equivalent circuit. So I think that's all. And thank you for listening. Actually, by the way, if we can also check how to solve I8 on the previous part. So if I just want to share it here, actually we can already solve I8. Okay. Okay, here in this part. Since we already know that the current flowing in this circuit is 0.5, so since this is series, from the simple equivalent circuit, this one, so 0.5 ampere is the same current that is also flowing here, which is R8. So actually we already know the current, the value of current that is flowing in resistor 8. So just to validate the solutions earlier using KVL, and it satisfies also. We computed and we checked that I8 is equivalent to 0.5 ampere. So this is checked. Okay, so this is a continuation on the problem that I presented earlier. So we have these given circuits on series parallel combination. We solve the circuits using KVL and KCL. And as I've said, we're going to validate the result using the simulator. So as we observe, it satisfies and our solution is correct. So as we all know that the total current flowing in the entire circuit is 0.5 ampere. And as we check, I1 is equivalent to 0.5 ampere, or that is equivalent to 500 milliampere. I4 is 0.25 ampere, and that is equivalent to 250 milliampere. And also the current flowing for R2, our R2 is 0.15 ampere, or that is 150 milliampere. 0.1 ampere for I3 at 45 ohms resistor is equivalent to 100 milliampere, or that is 0.1 ampere, and the current entering is 100 milliampere, and 150 is equal to 50 milliampere, or that is equivalent to 0.5 ampere. The same current also that will flow towards point D, this one, point D, and also 200 milliampere or 0.2 ampere across R5, and we have R7, 20 ohms, that is 0.25 ampere, or that is equivalent to 250 milliampere. So it satisfies the condition, or on the KCL, that the current entering is equal to the current leaving. So by the way, I am using this simulator. I just downloaded this one in the internet. Okay, so that's all. Thank you.